Okay, great. The next talk is split between two presentations, which will have even length. The first is going to be given by Jacob Bulmer, and the second by Benjamin Villalonga on the general subject of classical simulation of Gaussian boson sampling.
Great, thanks for the introduction. Yeah, it's a real privilege to be here at QIP to tell you about our results on the boundary for quantum advantage in Gaussian boson sampling, which is a project done with these 12 people here across the University of Bristol, Imperial College London, and Hewlett-Packard Enterprise. There's this paper on the archive, and also we were recently published in Science Advances. As Bill said, this is a merge talk, so in 10 minutes I'm going to hand over to Ben, and he'll tell you about some results from the team at Google on a similar problem. So in this talk, first I'll introduce Gaussian boson sampling, but I won't dwell too long on that because we've already had some really nice introductions already. I'll also review the state-of-the-art experiments, which we've seen a little bit of too. Then I'll talk about our results, which are on new exact simulation methods for the problem. And then I'll talk about how these results perform, and then we'll hand over to Ben. But first, I want to highlight the differences between my part and Ben's part. So in my part, we'll be talking about faster exact methods for this problem, but these run in exponential time. And then in Ben's part, they're talking about approximate results, and these run in polynomial time. Okay, so we've heard a little bit about this thing on the left, which is the original proposal from Aronson and Arkhipov. We have single photons going in, transform linearly, and then we detect them. The amplitudes in the Fock basis at the output are given by matrix permanence. This gives rise to a sharp P complexity for the classical simulation, like calculating the permanent, which gives rise to this sort of complexity arguments about the problem. In Gaussian boson sampling, we replace the single photons at the input with squeeze states. And the way that I want you to think about squeeze states in this talk is that we just have this coherent superposition of generating different numbers of photon pairs. And then we send these through some interferometer. And an interesting thing about this experiment is that just before the detectors, we can represent the state using the Gaussian formalism. And this is like an efficient representation of the state. So in boson sampling, you can think about the interference as being represented by a bipartite graph, where our vertices are given by the photons at the input and the output, and then the edges are the matrix elements of the unitary transformation. And then because the photons are indistinguishable, when we see some pattern, we have to consider all of the different perfect matchings on this bipartite graph, and I've highlighted one here. And so we sum over them, and this is where the permanent comes from. In Gaussian boson sampling, our photons were always created in pairs, and so we can think about how at the output of the experiment, we can pair the photons together. And so now we have an arbitrary graph where the perfect matchings correspond to how we're pairing up photons at the output. Summing over perfect matchings of an arbitrary graph is given by the Hafnian, so that's where this comes from here. And something I also want to point out is that we have half as many vertices in Gaussian boson sampling as we do in normal boson sampling for the same number of detected photons. And you can kind of think about this roughly as saying that in Gaussian boson sampling, we need twice as many photons as we do in regular boson sampling to have the same complexity. So now I'm going to tell you a little bit about these really amazing experiments that came out of USTC, which are called Yuezhen. So we send in into 50 modes of the experiment, we send in squeeze states, and then we have a passive fixed interferometer. And then at the end, we measure with threshold detectors. So these can only tell if 0 photons arrive or more than 0 photons arrive. There's two versions from this science paper and then a follow-up in PRL. In the first version, we have 100 modes. Our average, we see 43 clicks. And then in the second version, we have 144. On average, we see 67. And there's also various fidelity improvements, for example, lowering the loss and improving the sources. So now I'll tell you about how we simulated the experiments in our paper. So it's based on this paper, which was developed in parallel to our results. And I'm going to call it the measure ignore chain rule. And here we leverage the Gaussian state formalism to allow us to simulate the sample sequentially, one detector at a time. And we do this in a way where we only have to consider calculations on pure states. And to do this, what we do first, instead of measuring in the photon number basis, we measure every mode in the coherent state basis, sometimes known as heterodyne measurement. And then we immediately start ignoring these measurement outcomes. So we ignore the first mode, and we instead simulate it in the photon number basis, where we condition the first mode state based on the output measurements on the rest of the modes. And this is efficient to compute for the first mode because we just have a single mode Gaussian state. And we can do this, calculate the distribution for that mode, sample from it, and we get some outcome. Let's say it was 2 photons. And then we do this for the next mode, whereas here we now have a 2-mode Gaussian state, but we can compute the joint probabilities fixing the outcome of the first mode, get some distribution here, sample, and then we sort of proceed, and eventually we'll have a whole sample for the experiment with some pattern. And the complexity here is dominated by the complexity of computing the amplitude of the event that we've sampled. So another result that we used in our paper, and this was sort of original to our work, is on how we simulate these threshold detectors. So like I briefly mentioned, threshold detectors have 2 possible outcomes. Either they're going to be telling you that you saw vacuum, or you saw more than the vacuum. And so we simulate this with a trick where instead of simulating this threshold detector, we simulate a fan-out array of photon number resolving detectors where we imagine some sort of setup which will probabilistically scatter photons into one of these detectors in the array. We can use the algorithm that I just told you about to go through this sequentially, except now, as soon as we see a single photon within the fan-out, we can ignore the rest of the modes because we know that anything happening here is not going to change the outcome. We've still got a click. And this gives us a really big improvement in the complexity because instead of simulating this mixed measurement operator of the threshold detector, we're now simulating this like pure projector of a single photon, which is much more efficient. And we find this kind of quadratic speed up in the O-star complexity. So we took these ideas, we implemented them, and we ran them on a 100,000 core supercomputer, choosing parameters for like squeezing and loss and the size of the experiment, similar to the first version of Yuezhen. And we managed to sample 1,600 samples in 3.5 hours. And then there's some results here. So the distribution for the total number of clicks in our samples follow what we'd expect to see. And then we can also fit the runtime of our algorithm, and we can use this to extrapolate into like bigger experiments and so on. So if we do that, and we also extrapolate to running on Fugaku, which is the world's largest supercomputer, we find that we could predict that we would simulate the first version of the experiment in 127 milliseconds per sample. We can compare this to the experiment, which ran in 4 microseconds per sample, and the prediction in their paper, which we can scale to be about 12 years per sample. And this is a 1 billion-fold speed up on the classical algorithm performance compared to the previous prediction. If we do the same kind of thing for the second version of the experiment, we see that they predicted to be like maybe more than 100 billion years per sample, which is clearly a very big number. And we predict this to be about 3 hours per sample. And this is 1 quadrillion speed up. So in summary, there's some new exact methods for simulating Gaussian boson sampling, which perform quite a lot better than the old ones, particularly this quadratic speed up for simulating threshold detectors. And yeah, I guess the highlight result I want to tell you about today is that the latest GBS experiment can be simulated exactly if we had access to the world's largest supercomputer in 3 hours per sample. And then there's further work on trying to incorporate errors in the experiment to speed this up. And we'll also hear about some approximate methods now from Ben. There.
Thank you, Jake, for giving an introduction. Let me change the spot of the mic. Thanks for giving an introduction to boson sampling, to Gaussian boson sampling, and to my talk. That saves me some time also. So this is work we've done at the Google team, at the Quantum AI team, and work that you can check on the archive posting. And as Jake mentioned, he's focused a lot on exact methods to sample from Gaussian boson sampling distributions, similar to the USDC experiments. We have focused on approximate methods, trying to, by construction, create methods that run in polynomial time. And so the outline for my half of the talk will be the following. I'll give a little introduction on the setup and some concepts that are going to be important in the experiment and in our adversarial proposals. Then I'll jump into the methods, or in other words, the family of efficient classical samplers that we introduce. Then I'll jump into verification and results. So that is, how do we assess the quality of the experimental results versus the quality of our classical simulation results? And then I'll just give you a summary of conclusions and open questions. So let me walk you through the setup that I have in mind when I talk about this work. So we've already heard many times what Gaussian Boson sampling is about. Let me just emphasize the game that all of this is about. So we have a linear interferometer, at the output of which we have some threshold detectors. And I'm going to focus only on threshold detectors, even though the methods might generalize naturally to number resolving detectors, but we haven't explored that space yet. And at the end of this experiment, what you're measuring is either photons or no photons. So you get a very large bit string. In the case of the USTC experiments, a bit string of either 100 bits or 144 bits in the second version of the experiment. And when you do this many times, you end up with a lot of bit strings. And the claim is that these bit strings are coming from something close to the ideal distribution that you want to sample from. Now, this ideal distribution by construction is sharply hard to compute probabilities from. And so that's the whole point of the quantum advantage. But the experiment really is noisy. And so it's not sampling really from this QZ, where Z is a bit string. It's sampling from an approximate distribution that we're going to call P sub E, which has noise, has imperfections. And also it's important to emphasize the ground truth that I consider has some loss in it. And then our game as a classical adversary is to sample from another approximate distribution, P sub M, where M comes from mock-up distribution, from a classical algorithm that hopefully runs in polynomial time in the size of the system. And hopefully it does better according to some metrics of distance or some metrics of quality than the experiment. And there is two key points to keep in mind during this talk. And there is two regimes in which computing probability is actually classically accessible. It is easy to compute probabilities with low click number. That means with low number of photons detected. So keep that in mind. The complexity is actually exponential in the number of ones or the number of clicks. And the other regime in which this is simple is for low order marginals. That means if you constrain yourself to a small subsystem of the full distribution, it's easy, actually exponentially hard in the number of modes that you constrain yourself to compute probabilities. We're going to leverage these 2 points in two situations. And it's worth to mention that these two facts don't apply to random circuits or to quantum circuits in general. So we're going to use this in how we build classical samplers. We're going to use the second point, and both the first one and the second in our verification techniques. So let me walk you through the main idea of how we build efficient classical simulators or classical samplers. I'm not going to go too much into detail given the low amount of time, but we start from a description of our Boson sampling experiment, okay, which tells us how to compute probabilities, even though that's going to be exponentially hard. And we're going to play the following game. Since we can compute low order marginals very easily, how about we compute all the lower order marginals for some low orders up to an order k. So let's say we take up to order 2. And now we find another distribution that fulfills these constraints. Okay, my mock-up distribution is going to satisfy the low order marginals up to the order I want. And this is, of course, an unconstrained problem, under constrained problem. And one of the solutions is the ideal distribution, which we're not going to sample from. We've explored two alternatives. So that's using Boltzmann machines to reproduce these constraints. And we also came up with another approach that we call the greedy method to do the following task. And now, once we build the distribution, we can sample from it. And we build simulators for which we can sample efficiently. And now our hope is that higher order marginals of higher order all the way up to the full distribution are very, very close to the ideal ones. Now, by construction, our samplers run in polynomial time, a polynomial of degree k, where k is the number of marginals, the degree of the marginals that we satisfy. Now, this is something crazy to do in general. And in fact, it doesn't apply to random circuits, since the low order marginals are uniform and just carry no information about the full distribution. But in this case, our insight for this working is the following. There is a measure of how much corrections you need to make on higher order marginals to capture their difference from what you would learn only from lower order marginals. And this measure is called Ursel functions or connected correlations. And what we see in practice is that these connected correlations really decay in strength exponentially with the order of the marginal we look at. And so our samplers are going to have the following property. They're going to sample very, very well with respect to measures of distance. But of course, they're not going to carry these higher order Ursel functions, which the experiment might carry an imperfect version of. And so how do we verify our results? Well, it turns out that when you look at experiments like the USTC ones, the samples that you get out have some distribution over the number of clicks. And in particular, the USTC team made 8 data sets available. So these are these 8 curves. And you can look at the low click number regions of these distributions and compute the cross entropy. Again, that gives you a sense of the quality of the samples. In particular, for 3 of these data sets, the full distribution fits in the region that we can check. So for 3 data sets, we check the full distribution in cross entropy. And what happens when we look at that and compare that to the experiment? Well, we can look at the difference in between the cross entropy of our mock-up samplers and the cross entropy given by the experiment on low click number regions of the sample space. And for all 8 data sets, we have samplers of order 2 and order 3 that are on par with the experiment. And they run in polynomial time, actually in quadratic time and in cubic time. And for 3 of these data sets, as I mentioned, we look at the full distribution. Then we can look at another measure of quality. We make use of the fact that low order marginals are easy to compute. So on those, giving a bunch of bit strings either from the experiment or from our mock-up samplers, we can estimate empirical probability distributions and look at how the total variation distance and the scale divergence change as we increase the order of the margin. And so that is what we do. In particular, for total variation distance, the difference in total variation distance between mock-up samplers and the experiment is going to be in our favor if this number is negative because of the way we define this difference. And we find again that for all data sets, our 2nd and 3rd order samplers outperform the experiment up to the size of marginals that we can check. That is up to 14 modes. The tendency keeps being favorable, but the statistical error grows in our estimates. We look at something similar with the scale divergence, actually divided by the number of modes. So it's an intensive quantity, and we see the same. The difference is favorable to the mock-up samplers, and it stays stable as we increase the size of the margins. And so let me leave you with some conclusions. In this talk and in this paper, we introduce a family of efficient by construction Gaussian boson samplers. The approximation runs in time polynomial in the system size for a fixed k, where k is the order of the marginals that we satisfy, and is exponential in the order of the marginals. The hope is that for lower order marginals, we can outperform experiments, which we did for some metrics compared to these USTC experiments. And also keep in mind that Ursel functions are not captured by construction by these samplers, but they are imperfectly by the experiment. This is a feature by construction. And the whole intuition there is that even though we by construction don't capture them, we capture the lower ones perfectly well. And so that is enough to have better quality outcomes in terms of distance and cross entropy. And some open questions remaining are the following. So this talk, as you realized, relies a lot on numerics. It would be nice to have an analytical understanding and bounds and so on of these kinds of methods and some guarantees. The effect of loss would be interesting to study in terms of the decay of Ursel functions. This family of samplers could be adapted to not only threshold detectors, but also photon number resolving detectors. We haven't explored that part. And finally, we do as better as we can in terms of verification, but there is still some lack of techniques to make them comparable to the nice techniques for random secret sampling, where cross-entropy benchmarking and fidelity go really hand by hand. So thank you very much for your attention.
Hey, thanks for the great talks. I have one question to each of you. So maybe the first question to you. Is there a way to incorporate noise somehow into your algorithm, like photon loss or so, to make it more efficient?
Yeah, totally. So in fact, we did incorporate photon loss in the work. I just sort of had to skim over it today. So to incorporate loss, it's quite simple. So loss is a Gaussian channel. And so you end up with a mixed Gaussian state. You can decompose this into a pure Gaussian state plus Gaussian noise. and then you simulate that by sampling from the Gaussian noise first, and this gives you a displacement on your pure Gaussian state, and then you simulate, instead of a zero mean Gaussian state, you simulate a displaced Gaussian state. And the way that we compute things, this doesn't change the complexity. So loss sort of comes to us for free.
So it doesn't help a lot.
And in fact, pardon? Oh, yeah, right. Yeah, right. And then there's other sort of errors that we could really easily include. For example, like spectral errors, where we could decompose each mode into like multiple spectral modes and then sample them separately and then just take the results and add them together. Mm-hmm. So that's something that like would be quite easy to add on.
But would that improve the complexity at all?
Yeah. So I guess, let's say you detected like 100 photons. If you model them all in the same spectral mode, you'd have to calculate this like big Hafnian or loop Hafnian. If you did this spectral mode, maybe like some of the modes would come in one spectral mode, some of them in the other. And so the largest Hafnian, like the thing that dominates in complexity, becomes easier.
Okay, and the question to you, do you have any leads on a better verification theory for Boson sampling?
Not me. I've thought about this for a long time.
Yeah.
The original experiments used cross entropy in the way we used it here, that is constrained to fixed click number sectors. We introduced these marginal sort of scaling measures. We couldn't go beyond that. It would be great if someone has more ideas.
Okay. Great, thanks.
So I have a question for Ben. So you mentioned that the high order, the high order Ussel functions are decaying exponentially, and I think this is a property that we have used to come up with the the simulators. Does this happen because the actual experiment is noisy, or is this an inherent property of the Gaussian boson sampling?
Yeah, this is inherent. Like when you look at the ideal distribution, this is what you see. But further, in these experiments in particular, loss is included in the ideal description of the probability distribution. So the linear interferometer matrix is not unitary, actually. It's something different because they included loss parameters in it. And in that case, you see a even faster decay.
I see. So if I understand this correctly, then the simulators, that we have come up with now, can be used to, I guess, approximate the ideal distribution as well?
So here we approximate the ideal distribution of these lossy cases, right? Now, if you sample really truly in lossless matrices, you can play the same game. You get some approximation, but it's very unclear what the bounds are and what the guarantees are.
I see. Okay, thanks.
In general, we don't have guarantees on how good these approximations are beyond just numerics and our analysis given a sampler. I cannot give you a proof of some, delta epsilon proof of where you would lay. Yeah.
Sounds good. Thanks.
So this is for Ben. So you talked about spoofing, I think, total variation distance, right? You talked about,
Yes.
I think, cross entropy within a sector.
Yes.
Right. But
and K-yield divergence.
Yeah, right. But one thing that I talked about in the USTC experiment was this hog ratio test, right? The sort of heaviest output generation. Does that fit into the sort of cross entropy spoofing, or is that completely different? And were you able to spoof that for one of the mock-ups?
Right. The hog ratio is so when you take cross entropy. Here, so cross entropy difference tells you, okay, if you get a negative number here, your mock-up sampler is winning. If you get a positive number, the experiment is winning. The hog ratio is simply making this a binary variable. If it's positive, it's a 1. If it's negative, it's a 0. So it's exactly the same. It's just telling you whether this number is positive or negative.
Okay, so you do think that your algorithm would be able to spoof the the exact test that they used in USTC?
Yeah. That's what we're doing here. Yeah.
Okay, great.
They used another test. They call it the Bayesian. Do you remember the name?
Yeah, Bayesian likelihood test.
Bayesian likelihood. In this case, it doesn't work. You need to know the probability of your mock-up sampler. In this case, we don't know the probability of the mock-up sampler. We're just sampling.
Okay, great. If there's no more questions. Let's thank the speakers again.
I've been asked to make the announcement that if you have a poster, you should go put it up now.